Okay, we're going to get started. Take your seats. Hello, welcome to the second IRTF Open session this week. I'm glad to see you. My name is Dirk Kutscher, I'm the IETF chair. And so you signed up to our code of conduct and to our node well. So I leave this on for a second. So this is about IPR that if you are involved in anything or you know anything, inform us shortly. And this meeting, as all the other meetings, are recorded and live streamed. And so in general, the IETF has a set of rules that apply to these meetings. So in particular, the code of conduct, RFC 7154, and the anti-harassment procedures, RFC 7776. They also apply to us. And in addition, we have a code of conduct that is more specific on research ethics. So that's 9775. And yeah, the Internet Research Task Force is not doing standards. We don't have working groups. We don't produce standard tracks RFCs. So the purpose here is to conduct research that will hopefully be useful for the internet. And yeah, most of the work we do is done with the intent to generate insights for the community and, for example, enabling experiments. We currently have 16 research groups in the IRTF. 11 of them are meeting this week. Yeah, please look at the IETF agenda to find the meeting times. And actually, this is not a current slide. Let me skip this. I wanted to report on a few things that have happened. So we held a workshop at CONEXT in December last year on internet working challenges for AI, so a topic that we also discussed this week. Antoine Fresancourt, my co-chair there, and we published a report, which you see the link on the slide. If you're interested, check it out. We also held the HKUST Internet Research Workshop on Friday before this week. So that's a workshop that just invites ideas, lightning talks, and discussions on new topics or topics that people find particularly interesting. And yeah, it went fairly well, I think. So you see the photo there and topics that were discussed, IoT, computing, continuum, and the end-to-end principle, sustainability, source buffer management for low latency, and then some discussions on agentic AI communication. So we typically organize these workshops here in the area before the March IRTF, which is often in Asia. And so we likely do this again next year, maybe even for 2 days, depending on who can host us. So we will announce this on the IRTF announced mail list and other channels. If you are interested and in the area, feel free to attend that workshop. So it's open for everybody. You can just register and come. Okay. So as usual, we had the possibility to offer some travel grants for people to come to this meeting. So we offer travel grants to early career academics and PhD students from underrepresented groups to attend our meetings here and also the whole IETF. So the idea is, yeah, to make it easier to get people to attend the IETF, maybe for the first time or maybe first 2 times. And so these travel grants, yeah, pay for the travel accommodation and the IETF registration fee. And so the expectation is that people come and then stay here for the whole week, you know, make interactions with, you know, IETF, IRTF folks, attend our meetings, and then, yeah, find a good way to contribute. And so this has worked relatively well in the past. So many of the travel grant winners there were able to find a good topic that they could then later work on and then continue to attend the IETF. So we also offer travel grants for our next meeting. That is going to be in Vienna, not in March, sorry, it's in July. And the deadline is on March 27th. So that's relatively soon. So it's the end of the week now after the meeting. So if you're interested, please make sure you apply and share this information with people who you might think could be interested. And so we also have the Applied Networking Research Workshop every year at our summer IETF. So that will be next meeting in Vienna. So the co-chairs for this workshop are Thomas Schmidt and Suresh Krishnan, and there's a call for paper that is currently open. Deadline April 17th, and yeah, please submit your best work in applied networking research to ANRW. It's a really nice event, so it's like one day during the IETF week. Right, and yeah, so we have the Applied Networking Research Prize, ANRP, where we want to recognize the best recent results in applied networking. So the idea is that, well, there is, you know, good published work in, let's say, top-tier conferences, and we'd like to bring that to this community, and you know, maybe to you know, encourage more discussion about this. Maybe this could start up some new work in the IETF, or it fits into things we are already doing. And yeah, it is also comes with so support for attending our meetings. So we had 17 nominations for this year, for 26, and we made 6 awards. And then at each meeting, we will present 2 of these papers and invite the paper authors to present here. Yeah, we have a very supportive award committee. Thanks everybody who helped with selecting the papers. And so the ANRP is kindly supported by ISOC, Comcast, and NBC Universal. Thanks very much for the support. And yeah, today we have 2 exciting talks on the agenda. So first one will be by Tianyi Gao for his work on transport level encryption for data center networks, and second talk will be by Xiangjie Huang for his work on sending burstiness control for high quality real-time communication. So we will have these 2 talks now, and then after the talks, I'd like to continue the discussion that we started yesterday on internet work challenges for AI. So we had a dedicated meeting with also really good presentations, ideas, and yeah, some good discussion that kind of crystallized on I think, few good topics, and we just like to use the rest of the time today to discuss this more with you. And so now I'd like to welcome Tianyi Gao. So his paper title was Designing Transport Level Encryption for Data Center Networks. And Tianyi is a PhD student at the School of Informatics at the University of Edinburgh and supervised by Michio Honda. And he received his his master degrees in computer science at Edinburgh as well with class prize. And previously he interned under Professor Wang Yusan at the Advanced Institute of Information Technologies in Peking University. So his work focuses on designing high performance and secure data center networking systems. And he's currently working on SMT, a data center transport protocol with transport level encryption that is designed as a generic secure transport that can provide strong confidentiality while maintaining low latency and high throughput for a wide range of data center applications. And he also contributed to XO, so a framework for remote TCP connection offload that improves scalability and reduces host overhead. Welcome, Tianyi. Give me a second. Bring up the slides. Okay, welcome again. Looking forward to your talk.
Hello. Yeah. Thank you, Doug, for introducing. So everybody, I'm Tian Gao. I'm a fourth-year PhD student at the University of Edinburgh. I'm here to present my work on design transport level encryption for data center networks. This work is being done at the University of Edinburgh with my colleagues. This paper is going to be appear at the IEEE Security and Privacy later this year at May in San Francisco. So let's get started. So first, let me introduce some background of the encryption in the internet. So before 2010, the encryption in the internet, people already starting to aware, but encryption was exceptional. It's quite rare. The major change point was after 2010, Google started roll out the default SSL encryption. Then there's more wide adoption of the encrypted transport like SSL and TLS in the internet. Then later on, in most recent, people start try to encrypt everything. Like also there are encrypt native transport design like QUIC and ECH, and people put DNS over HTTPS. And the most recent, people start work on post-quantum resistant encryption methodologies. But how about the data centers, right? That's the internet. Everyone knows internet is not safe. But is data center really safe? Of course not. In 2013, Snowden revealed that NSA actually captures all the intra-data center and inter-data center traffic. Some people start to realize that we need actually encryption even inside data center. And that's what happened today. Like TLS also being used in the data centers, microservices. As we can show, this Meta have their post about their practice of using TLS in their data center. And also, it's quite trivial that their data center is not really trustworthy. They may be malicious insiders and compromised tenants, which also makes us to understand that we need encryption in the data center. However, the encryption protocol currently being used in the data center are mostly TLS, and that's based on the TCP, which is unfit to data centers. In the data centers, the major workload is RPC, and we need high throughput, low latency RPCs for small and big messages. And for that, software overhead and head of line blocking really matters. Let me give you an example. So now we have several servers. For example, one client send a request to one server, and this server partitions the request to several servers. and these servers they respond the reply to this server. But if, like for example, one of three are slow, then the server in middle have to wait until the one of the struggler to come, then to reply then do the reply. That's what makes like tail latency is very important in the data center. And but why in data center, particularly TCP TLS, can have head of line blocking problem? So for example, one example would be packet loss. For example, if we multiplex messages on just one TCP connection, if one message is lost, the application have to wait until this message before hand over later message which already arrived. And another example would be a large message in the flow. So the smaller message later on have to wait the previous big message fully received. And also, like even if we just we don't multiplex messages over one TCP connections, we make TCP connection just serve single message. The connections themselves will need share the same CPU cores, and another connection may be delay one connection because they are sharing the CPU cores. That's why I want to solve this problem. That's why I designed SMT, secure message transport, and the SMT have several goals for its design. First of all, because it's a secure transport mode, secure message protocol, we of course want to make it to be secure. So we aim to meet TLS same security guarantees as TLS 1.3, and based on same trust model, but with a message-based abstraction. So what a message-based abstraction looks like. So this is how our SMT packet looks like. We have a source port, destination port, message ID, and message length in the transport layer header. And in the application layer, we also have a message framing header, which indicates the message, the offset of the message. And by using the message-based transport, we can avoid head-of-line blocking by sending the message out of order. And also, SMT can leverage existing hardware offloading opportunistically. So we already have TCP segmentation offloading and TLS offloading for TCP, but we also want to utilize it. And also, SMT, we didn't encrypt the message, the transport header like quick. We want to keep it as plain text because it's in the data center. We have less attackers in general. But we actually really need in network computing, so we can load balance the messages in a fine-grained way. Okay, and we design SMT as shown in the figure. We lay it as same as like a new transport protocol. We didn't design it with UDP encapsulation to make use of better hardware, and also it's we want to really design as a new transport. Some people may ask, why not we just use Quick then? But actually, Quick doesn't fit. Quick is designed for the internet, where the latency is millisecond level, and the head of line is mainly on the path, and there are a lot middle box in the internet and old hardware, which interferes a lot. And for the hardware offloading, because many Quick users are actually client device, so the hardware offloading isn't that essential. The load is not high. But for our protocol SMT, we are expected to run in the data center where the latency requirement is microsecond level, and the head of line blocking can happen on both paths and also the cores. However, in the data center, it's a more controlled environment, so we have less middle box interference, and also to support the high throughput and low latency RPCs, we really need hardware offloading. And what about other options since QUIC doesn't work? So there were like proposals for encrypted transport like TCP Crypt and TCP/LS. However, their common problem is they both inherit the TCP problems, which is fundamental head-of-line blocking. But there are also proposals for message-based transport, but they are not encrypted. For example, SRD from AWS and Falcon from Google. However, they are both hardware transport. They really they depend on the hardware a lot, and they are not generic. There were generic message-based transport proposals from the academia like NDP or HOMA. Among them, HOMA provides a generic message-based transport interface with a reasonable Linux implementation. So our idea is we use HOMA as a middle ground to design a encryption message-based transport. And since we want we already have HOMA, we already have TLS, why not we just stack TLS over the HOMA, right? Actually, that doesn't work because TLS assuming in order byte stream as its. So for example, here, if we did one TLS handshake, then we just encrypt the message. For example, we have there are three messages. We just encrypt with record sequence number 0, then 1, then 2. But actually, because message-based transport, we are sending the messages out of order and receive out of order. So actually, a later encrypted message can arrive earlier than but the receiver don't know. Receiver still try to decrypt with an earlier record sequence number, so the decryption will fail. And another option would be we just do a handshake for each message, but that's really, really too slow. So let me introduce the architecture of SMT. So for SMT, we first do the handshake in the application. So we assume application already agreed on key pair beforehand. Then application will set the we are a non-encrypted message-based transport. Then application set as a key to our transport. Then application can just send the plain text messages in different size to the SMT socket, and SMT will deliver them actually on the wire concurrently and encrypt them inherently. For example, like one box here is just like a packet which have a message ID, message length, and the offset payload. The offset and the payload actually encrypted. Okay, there are two main key design components of SMT. The first one is message format. We based on the TLS record layer protocol. So because we want to preserve existing TLS offloading with TSO. And the second one is per message record sequence number space, where transport integration enables replay protection to achieve similar security guarantees. So let's dive into the SMT message and packet format, how we reach the goal of we enable the TSO and with TLS offloading over a message-based transport. So let me first explain what is TSO and TLS offloading. Just we see on the left hand side, there's like a big packet with a header, and when we send this big packet with header into the NIC, then the NIC will chunk this big packet into MTO-sized packets. Meanwhile, copy the headers into these packets, and it will do the encryption at the same time. So our key finding is that we found out that the TLS offloading with TSO, which was originally invented for TCP TLS, it actually works for non-TCP packets. I mean, the protocol number in the IP header is not TCP. It actually works, and but the header, the transport header format need to be kind of like TCP. So that's why we have this packet format for our SMT protocol. So we have a protocol number not equal to TCP in the IP layer, and in the transport layer we have message ID, message length, and also there's one thing called TSO offset. I will explain later. So for example, we have TLS records warped up with message offset and actual message payload, and one TS and so one packet payload can look like this. One packet can contain one TLS header, message offset, and message payload, and the packets inside a TLS record can just have a message offset and a message payload, and so this is a TLS record, and one TSO segment can have multiple TLS records up to 65K bytes. So now I'm going to explain how the actual segmentation and reassembly works for SMT protocol in action. So now we have one message over two TSO segments, which each with one TLS record. So you can see on the right-hand side, we are on the sending side. So after the packet goes through the NIC, it become like this. It trunks it to the MTO size, and each TSO segment is chunked to 3 packets. One packet with TLS header, one packet without any TLS stuff, and one packet with TLS trailer, and then these 2 sets of 3 packets reconstructed back to TSO segments, but actually encrypted. Based on the IP ID and the TSO offset, we actually set in the sending side. Then we can do the decryption. It will decrypt the encrypted part based on the non-TLS record sequence number. Then we have like similar to the right-hand side, right? Then we reconstruct the message payload itself based on the message offset header. Another main component of SMT is per message record sequence number space. Because our goal is we want to do out of order message delivery, but the problem is multiple sequence number space. If we just share over one TLS handshake, it can create like duplicate sequence number, which actually breaks the replay attack prevention provided by TLS. So our solution is we can avoid the duplicate by containing with a unique message ID in the session. We composite the so there is a 64 bits record sequence number field in the TLS TCP. So we put the message ID inside the higher bits of this field, and we put the index of the records within the message in the lower bits. So right-hand side is an example. For example, we have 3 messages, and the message 0, it have, so the first record of message 0 have index 0, and the second one is message 0, index 1. So it will use the record sequence number field 0, 1, and the same applies to other messages. However, this leads to another problem, which is we need to trade off between the message size and the how many message we can serve in one TLS handshake session, as we are splitting the record sequence number field to 2, one for message ID and one for record index. So the bit allocation can be flexible to support larger message size. For example, if we look on the figure on the right hand, if we have less bits for the message size field, we can handle more messages per handshake, but the maximum message size gets smaller. Like, for example, if we only have 8 bits for the message size field, we can only have the message size at the biggest only 400K, which is not good. So currently we opt for the right circle point. We allocate 16 bits for the record index and 48 bits for the message ID. In that case, we can support up to around 100 megabytes message size at maximum, and around 300 trillion messages for one handshake session. So SMT, let's overview. So we can see that SMT compared to TLS 1.3 actually provides same authentication and confidentiality, and it also actually adds up HOMA for its integrity check, as HOMA didn't provide any checksum thing. And because the order in the SMT is per message, we only have order within each message, and inside each message, the record index will monotonically increment. And for the replay attack prevention, we have this composite ID thing. We guarantee that every message ID can appear at most once, so we have a unique space. And for the length concealment, we can still preserve the existing TLS padding kind of mechanisms. To support TLS offloading, so TLS offloading in the Mellanox NICs was designed for in-order delivery, but to support TLS offloading for out-of-order delivery, we meet such another main challenge. So the per message record sequence number is essential for TLS offloading, as the NIC expect in-order record arrival. Like, NIC have its own counter for TLS record sequence number. So every time there's a packet coming in, the counter inside the NIC will increment by 1. But we actually can update the counter inside the NIC, but it's not automatically. For example, here we can attach a dummy packet before the actual record, like S1. We can update its counter to 1, and for same apply, like if we can attach this R3 to update the NIC counter to 3. So, and the message-based transport, but the message-based transport can actually send the messages in any order. For example, if we have 2 cores sending S1R1 and S3R3 together, then the actual it will be serialized maybe S1R3 or something, and it breaks the counter synchronization. And that's why we need per message record sequence number to allow such sender to use separate flow context. For example, here we use C1 and C2 as separate flow context or in crypto engine to encrypt the NIC, so NIC have separate counters for each message, and we recycle it. The implementation of SMT is currently around 3,000 lines of patch upon the Homa Linux kernel module and 300 lines of code on the Mellanox NIC driver to support the encryption offloading. And it's currently open sourced on this link. We are working on the next version for better, for more features and better performance. So this now let's go through some evaluation briefly. So we can see that so we compare the SMT with existing TCP KTOS with both offloading TOS offloading enabled and disabled, and we can see that SMT for unloaded latency, we can see that SMT outperforms TOS by 20 to 30% with hardware offloading and 16 to 35% without it. And we also did experiment on the loaded throughput for different number of concurrent messages and different size of messages. We can see that for smaller message, 64 bytes, SMT have 16 to 40 improvements, and the same apply to 1 KB. However, for larger messages, because Homa is not really optimized for large message, it's slightly slower than existing TCP TOS, but we are working on it. We also ported the SMT to actual applications. For example, we ported to the Redis, and we show that SMT actually outperforms KTOS by 5 to 13% with TS offloading, and 8 to 70 without it in different workloads. Also, we also show the SMT performance for in kernel application, not only user space applications. We ported the NVMe over Fabric for SMT and compared with NVMe over TCP. We show that for P50 latency, there is up to 77% improvement with offloading and 50 without it. And we show even better performance. We show even more improvement on P99 because SMT works better on tail latency. So we have up to 16 and 21 with or without TOS. Here is some discussion and future directions. So the SMT ensured the message integrity which Homa lacks, and as I mentioned before, we currently still using IPID to reconstruct the chunk the packets of the message, but IPID doesn't exist in IPv6, so we can only have a TSO segment which at maximum size of 2 MTU. So we want to solve it somehow. Maybe we can have some indication in the TCP sequence number field for non-TCP packets. And another thing is the receive side offloading. So currently SMT can only do standard-side TLS offloading because we are unable to let the NIC just we are unable to indicate the NIC in decrypt packets that's not TCP unless we can modify the firmware. So we are working on this. And another thing is the PSP. I don't know whether you know PSP. PSP is like kind of like IPsec kind of thing. So we are also thinking of supporting PSP. And also, because we preserve the plain text message ID and message length, we are planning on more like in-network computer applications, like and work with the MTP, which is a protocol present in SDI 2095. And also, regarding post-quantum questions, SMT is automatically post-quantum resistant because it's just for the handshake part, it just follows TLS handshake, and the cipher we used is just AES GCM 256. And the conclusion is a secure message transport. SMT is a message-based encrypted transport for data centers, and we have already in Linux kernel implementation as Homa Linux extension. We are also working on BSD implementation. I have colleague will present in the BSD scan later this year, and the ongoing work is we are improving the performance and the implementation, and we are trying to submit internet draft for SMT for next IETF. Please see more details in our papers, and also I'm very, very happy if you can come me in person, we can discuss. And also super happy for any criticism. Okay, thank you.
Thanks.
Thank you very much.
Thanks, great work, Kenny. Okay, yeah, we open the questions, and that was Rod.
Hi, Jenny, thanks. That was a really good talk. And just from a quick look at the paper, it looks really good. I actually want to go back to the underlying assumptions about this. Have you guys done any work on actually analyzing whether or not there are actual existing threats in the data center environment? How strong is the underlying proof of the motivation for doing this work?
So the basically existing data center network they already mostly adopted the TLS actually. After the NSA thing, the Google and the Meta, they all have their own way to do encryption in the data center, and there are also literature that shows inside the data center, particularly multi-tenancy cloud, that the tenant can be compromised, right? And there are also zero-day attack threats that there are ways to actually escape the code from the hypervisor, from the virtual machine to the hypervisor. Then it can snoop the packets from other tenants.
And so that's actually an attack at the packet level on the wire, as opposed to cross VM.
For cross VM, there are different vendors, and you don't know whether there's bug on the vendor side, right? Like for
between virtual machines inside the same node. Seems like actually the bigger vulnerability to me, but
yeah.
Thinking about this, I haven't looked at it, so I don't know.
Yes, there are.
Okay.
Stuart.
I'm Stuart Cheshire from Apple. Thank you for this presentation. I have a couple of suggestions of things for you to look at and explore. One comment I have is that ever since I was a student, people have been talking about head-of-line blocking being a problem. And it's the kind of thing where you can draw a picture and see that it seems like a huge problem. And it's really unfair that these packets are waiting because of head-of-line blocking.
Yes.
But the question is how often that happens. And I did some work years ago with a professor from Franklin and Marshall College in Pennsylvania, a guy called Jana Iyengar. And if you look for expired internet drafts with Minion in the name,
yes, we know Minion.
Okay.
We know Minion, but Minion is also and we know Minion. Minion have like you have like a separator between the actual messages, but we still found that the minimum need still based on TCP, and the minimum need some modification on the TCP, and which is kind of hard. So we found it maybe it's easier. We just have a new protocol, right? Instead of a hack TCP.
So you answered one of my questions, which is you're aware of Minion, which is
yes.
that it had some similarities that it wasn't really TCP, but it kept the TCP header format so that things like TSO could be used.
Yes, we actually, our work is inspired a lot by Minion. Thank you.
That's nice to hear. We implemented that. Jana actually did a sabbatical at Apple, and we implemented it. And one of the reason the drafts are now expired is because we found that There were lots of teams at Apple who thought they wanted out-of-order delivery. And when we gave it to them and they tried to use it, they found it's much harder than they realized to actually write their code to handle data when it's out of order. And that code is hard to write, and it happens rarely, so that code doesn't get very well tested. And just my last comment on the subject of it being rare, head-of-line blocking is caused by packet loss. And you started off by talking about that. The question I would ask is, how common is packet loss in a data center? Because if you're running your data center right with DC-TCP, there should be no packet loss. And
Yeah, packet loss is not that common, but there's still like a large message, delay other later messages, and the one connection. So another thing is like if you consider a call handling the TCP connections, so we can only do load balancing for one. If we do load balancing on TCP, we can only do per connection granularity, right? So we cannot like just dispatch the messages to different calls. So that's actually a fundamental reason that on computing wise.
all right, thank you.
Hello, Antoine. I read your article several times and it's very nice.
Oh, thank you.
I have two questions actually from reading and looking at the presentation regarding the fact that in data center and in your design goals, you target establishing exchanging message in data center with very low latency.
Yes.
The first is you rely on TLS for key exchange.
Yes.
And
yes.
Isn't this introducing a long delay to establish the key at the beginning of the flow establishment?
So yes, I mean, we need some way to have agreed keys.
Okay, so then you do 0RTT and...
we can have resumption for later flows, of course. But I mean, we need a way to exchange keys. TLS handshake can be one way, or we can have pre-shared key, whatever, as long as we find a secure way. And I think the TLS is the most common standard for handshake nowadays.
The other one is in the design of your protocol, you make lots of design decisions around the fact that you're going to use TCP offloading capability for encryption. And why didn't you use a lower level offloading, like the cryptographic function offloading directly from a custom design protocol that you are going to do anyway?
So the key of doing that is because of we want to do the TSO segmentation and a TCP segmentation and encryption together. So we just give it to the NIC, and the NIC just chunk and encrypt. So if we do, of course, we can do, we let some encryption engine like Intel QAP kind of thing to do that. But that actually is still like we need to call them and get it back, then give it to NIC. That actually adds up latency. And since we already make it working, why not?
Okay, my assumption was that the second way would be lower latency, but if it's not, perfect.
And no, I think we didn't add encryption. I think we didn't. So our hack didn't introduce more latency compared to TCP vs TLS, as it's shown in the figure. So we actually, because our stack is lighter than kernel TLS, we actually have lower latency add up on the plaintext transport.
Okay.
The way we made Mellanox NIC work with message-based TLS offloading didn't actually introduce more latency compared to TCP TLS offloading.
Okay, perfect. Thank you.
Okay.
Okay, let's thank Tianyi once again for the great paper and the very nice talk.
Thank you very much. Thank you. Thank you. Thank you. Thank you. Thank you. Oh, okay. Okay.
Thanks for talking.
Thank you very much. Thank you, everyone. Thank you. Please talk to me if you have any more questions.
Yes. Okay. Okay. Now I'd like to welcome Xiangjie Huang. So Xiangjie Huang is a first-year PhD student at HKUST, advised by Professor Zili Mang. And prior to starting his doctoral studies, he obtained his master degrees with a focus on video coding. He's deeply passionate about advancing next generation real-time communication systems and improving them in every possible aspect. And today he will talk about ACE, sending burstiness control for high quality real-time communication. Welcome, Xiangjie.
Thank you, Professor Koster. And let me figure out how to use it. Okay, good afternoon, everyone. So, my name is Xiangjie from Hong Kong UST. And it's a great pleasure to me to have this, I can deliver this talk to you guys. I'm a first-year PhD student in Hong Kong UST. And this work, ACE, is published in SIGCOMM last year. And in this work, we made some improvements to the real-time communication system. And real-time communication compared to like data center network is a kind of a niche field. So I'm glad that I can share with you some of the experience of how we improve it to you guys. So this paper, ACE, we made some improvements, and to do this, we proposed a new control dimension. We call it sending burstiness. So in this talk, it's not a conference talk, so I want to discuss with you guys about some of the like real world motivation behind it, and some of the experience we had when we want to apply it to the like large scale deployments. So let's get started. First, real-time communication. Some of you guys may be familiar with this term, some of you may not. So I will explain briefly. So real-time communication, RTC, is the video transmission protocols or techniques under a lot of daily used applications. For example, the daily video phone call when you want to call your friends in a video mode, and the video conferencing that we are using every day and we are using now. And there are still a lot of other applications such as the emerging ones, cloud video gaming. Some of them are even future applications like the remote surgery, the teleoperations of robots and of the vehicles. And there are a lot of others that are not listed on the slide. For example, when you want to use the AR, VR for the streaming, when you want to stream a video from the AR, VR service to the like VR, AR headset. So real-time communication becomes indispensable in lives. And why it is hard, or what is different from this real-time communication between the other like video on demand or traditional video streaming? The main difference here is the communication in RTC is more interactive. Or in other words, when you want to like play video games on the cloud, the game service is run on the server. So every command you make from your keyboard, you want to get instant feedback from the server. In other words, you want to see the next render frame from the server. So that means the latency requirement of RTC is typically high, and there will be no buffer allowed when you are transmit these video streams in RTC. So that is the main difference. And in this slide, what I want to show you is the frustrating latency issues in RTC. So a lot of researchers, including us, we identify tail latency issues are the main blockage or the obstacle of the path of future applications. So here I list some of the papers. And as you can see, these papers are from the recent years NSDI and SIGCOMM, and they share one thing in common. They all have a large-scale measurement on the production level RTC applications. And you can, if you see the values they report for the tail latency metric, the values are still very high. For example, the paper, the third paper here, I don't know why the position is shifted, but for the paper, for example, for the paper tooth, you can see the store frequency you report is still 1 store event per minute. So it can translate to every minute you will have a user sensible video freeze. So imagine that if you are using this, RTC system to do a remote surgery, it can be considered not only a frustrating experience, but also very dangerous. So this actually directly motivate of we are going to see where is the latency come from, and it directly motivate this paper. So in this paper, we break down the latency into parts. So let me show you our evaluation on WebRTC. So this in this figure we show, if you will see the left side of this figure, it reports the scenario where the end-to-end latency is less than 100 milliseconds, or for those most of the cases. For the latency cases that are not in the tail. For most of the cases, you can see the latency components don't show much difference in proportions. But if you see those tail cases, or the cases where we have latency greater than 200 milliseconds, in the latency components, the pacing delay takes the lead. And this is our evaluation on WebRTC. And we also validate this data from the online data we collected from the ByteDance Douyin cloud gaming, which directly show that the pacing delay contributes to 100 milliseconds store. So what is the pacing delay here, and how it is formulated? And we can see it in more detail. So to introduce this in more detail, so let's first see the sending pipeline of RTC. So in RTC stack, it's across 3 layers, the application to the network layer. And there are 2 important components here. One is rate control, the other is video encoder. So ideally, the rate control constantly monitors the network, and it finally determines the rate. And the rate is set at the target rate of the video encoder. So the video frames we are going to transmit will then be compressed, followed this target bitrate, and then segmented into data packet, and finally sent to the network. So in that case, oh no, the slides don't have any animations, right?
No, they get converted to PDF.
Oh, that's it's fine. I'll just use my finger to point it. So okay, so let me back to the last slide. Oh, this one. Oh, thank you. Yeah, so the video will finally be compressed into packet and sent to the network. This seems fine, but in reality, the sending pattern is not that smooth as we think, because the videos are in frames. So it's this way. So in the real RTC sending pipeline, the frames will be captured frame by frame. So if there is a 30 FPS video, it will be 33 milliseconds each frame. So we will have a burst every 33 milliseconds. And in that case, this burst can be large. So think about it. If we want to stream a 30 Mbps video with 30 FPS, one single frame can be over 100 packets. So it will be tiny bursts across all the sending time scale. So these bursts can even be exacerbated by one thing. It's the content complexity. So if we think about the real video frames that are going to be transmitted, all of the frames are show different in the content. For example, for the 4 frames, the third frame here is actually different than the previous 2 frames. So it will result in an even larger frame size in the 3rd frame. So if we directly want to send this packet, send this frame into the network, it was considered risky. It was considered risky overshooting the bottleneck network, the buffers. So that's why a direct solution, a straightforward solution to this problem is we add a queue here. We just add a queue to the transport side. And we just set the targeted rate set to the video encoder to the output rate of this queue. In that case, the videos can be transmitted into the network very smoothly. So this sounds great, but as long as there is a queue, there will be possible delays. So, because there is no animation, I can just talk myself. So if it's just the average frame size, as you can see, if the dotted line is the average frame size, the delay of this queue will be at exactly the frame interval. But if the frame is large, if the frame is twice the average size, it will be twice the frame interval to be the delay of this queue. So in that case, the larger the frame size we have, we'll have a larger queue size. This is how the pacing delay that I showed in the previous slides coming from. Okay, and in this slide, I want to show you guys why this matters more today. Actually, I would forgive me. Actually, in this slide, there are three reasons, but they are just moved in the animation way. So there is only one reason presented. So the first reason is the network. So in short, the network RTT is shrinking. We can say thanks to the 5G, thanks to the development of network infrastructures, the edge service, the RTT is now shrinking, especially for the service like cloud gaming. So the RTT in the past is large, so the propagation delay takes the lead. But now it's the queuing delay. And if the queuing delay in this scenario, if the queue is formulated in the sender, it will be pacing delay. So this is the main reason why the pacing delay now is taking the lead. Another reason that we have is the content variability, even though we don't show here. So another reason is the content variability. So now if we are streaming a video, a gaming video, the content is moving very fast. So the fluctuation in the frame size will also be large. And the third reason we identify is the quality requirement that users have. Now users always require for the very high resolution videos. In that cases, the average frame size will be larger. Like if we are moving from the 1080p to the 4K video, the average frame size will be larger. So if we see the second and the third reason here, the average frame size is getting larger, and the fluctuation for frame size is also getting larger. So for the tail cases, we will experience a lot of occasionally experience a lot of large frame size that makes the pacing latency goes to the tail. So that's the trend. And how can we deal with it? So in this study, we want to firstly explore, is that a possibility that we can just let go these bursty frames? Letting go, I mean, just send it to the network, and we don't we don't really consider it. So if we just let go these passengers, let go these packets into the network, it will become a comparison between two queues. Because if the queue doesn't formulate in the sender side, it will formulate in the network side. So you can consider the buffer here. I mean, it will be the bottleneck buffer inside the network. So it will become the comparison of these two queues. First, let's think about the situation one. In situation one, the pacing rate is less than the network bandwidth. In that case, it is better to let this packets go to the network, because it will be faster to deliver those packets. So there will be no meaning to let these packets wait in the pacing queue. But there will be another circumstance. This should be finally to show up. Sorry. So another circumstance is the buffer, the queue size of the buffer here is unpredictable. So if we send a pretty large frame that fill in this network buffer, and the packet gets lost, or the frame length here is larger than the buffer length, then we will have subsequent retransmissions. In that case, the latency will go to tail. So it will be better to let this packet stay in the pacing buffer. So as you can see, and either ways, if no matter if we just let the packet go, or we directly keep them in the pacer, there is one conclusion: the lack of management to the burstness. So this is the main claim we have in this paper. So we want to manage this burstness that we can send into the network. So that's the key insight. So to do this in this work, we proposed ACE. And in this work, in the ACE, we want to manage the burstness from both NQ and DQ perspective of the queue. And as you can see, the ACE consists of two control mechanisms. One is called ACE-N. N means network side. So in the network side, we want to adapt the sending burstness. And in the encoder side, we want to adapt the encoding complexity to get a smoother frame size. So as you can see, the problem of the pacing queue is induced by the frame size. So we want the frame size produced to be as smooth as possible. And in the network side, we want to sometimes send burstly in the network, but sometimes keep it in the pacing way. So that's the main idea of of our ACE. And they work together and finally get all of this burstness being managed. So let's talk about some of the details in the network side. Firstly, the ACE-N, or the network side. In the network side, we want to control the sending pattern. And the main insight is that we want to adaptively control the sending burstness. So we ask two simple questions. The one simple question is the network buffer is empty? So if it is, it will best to let this packet go so we can burst more aggressively. And the next question is that risk overshooting the network buffer? If it is, it will be dangerous. So in that case, we want to shrink a burst packet and pace more strictly. And this guides us to have our design in ACN. So in ACN, we estimate a queue size to adapt a token bucket size. So we finally use the token bucket. This token bucket is to control how much burst you can let go to send it to the network. And we we adapt the bucket size, and we adapt the bucket size. And what's the input of our algorithm? We take the queuing size as the input. So ideally, we want to know the available token size, available queuing size inside the network. But that is not possible. We never know how many the queue size inside the network is. So the only thing we can estimate is the exact the real queuing size. So we estimate the queuing size and we increase to probe the bursty size. And if we detect some loss, we detect the queue, it means that it is more possible that the network queue is going to the top. In that cases, we will decrease to avoid loss. We did have a lot of other design to make this design more complete, and we can cover more of all of the corner cases. But in the design philosophy, or in the most simple way, it is our design on the ACN. So let's get next to the AC, the encoding part. So for encoder, our goal, our purpose is we want to reduce the frame size of the large frames. We want to make them as smooth as possible. So we asked the encoder, as you can see, there is a large frame here. So we asked the encoder, is there any ways you can make this frame size a little bit smaller? And the encoder says, yes, we do have some approaches. That is what I said, the current approaches. The encoders always wants to, if the encoder wants to make this frame size smaller, it will use the strict rate control mechanism. But this comes at some cost. If you're using the strict rate control mechanism, you will finally have you are actually get more lossy compression to the frames, and this will end up in a worse quality. This is not something what we want. In other words, if we treat those frames with a more lossy compression, we'll finally have a blur frame, and this blur will even affect the subsequent frames. This is not something that we don't want. And our evaluation even shows that the strict rate control mechanism will reduce the VMAP score of this frame of the video for 10 to 15 points. And what we choose to do is a different way. We adapt the encoding complexity to enable a smoother stream. So let me explain to you what the encoding complexity means. So actually, the encoding complexity is controlled by a set of video talking techniques. So more advanced video techniques we have, the coding complexity will increase, but the frame size will be reduced. And more encoding complexity we have, the encoding delay will increase. But because we have a less frame size, the pacing delay will decrease. So as you can see, there will be a trade-off. A trade-off here is possible. So if we can increase a little bit encoding time, but end up the queuing time be decreased, there will be a time saving. So that's the philosophy that we design for the AC. So we adaptively choose to control the encoding complexity to make the total time, including the encoding time and the queuing time, to become the minimest. And one last thing I want to mention is that in the AC control, actually 95% of the frames are fine. We don't need to adapt extra work of the encoding to control it. What only matter is the tail frames, or for the less than 5% of the frames. These are oversized frames that will eventually cause stalls, eventually cause the latency goes to tail. For those frames, AC will target this. We will spend more encoding effort to it to make the size smaller. So that's the key philosophy for the AC. And let me show you the evaluation results. The main evaluation was conducted by mahi-mahi emulations with the real-world Wi-Fi and cellular traces. And we compared ACE with some of the baseline, some from the encoding rate control mechanism, some from the WebRTC pacing or burst descending mechanism. And as you can see, ACE can balance in between. So for the best quality baseline is the native WebRTC pacing one. It shows a great quality. But as you can see, because of the large frames, the P95 latency is the highest. So compared to that, ACE can reduce latency for 33%, but it maintains the similar qualities. And for the strict bitrate follow baselines, ACE can have the similar latency. But the quality of it, because it allows the frames to observe the quality, the VMAP score here is like 12 scores higher than the baselines. So this slides just show that in our evaluation, and if we are trying to control the burstiness, the result will be superior to the pacing, to the both pacing and bursty, and the CVR, the rate control baselines. And in this slide, I want to show you what we found in different environments of in the experiment. And the key experience here is the sending burstiness control can benefit more in the Wi-Fi scenario and the gaming videos. The first, let's see the scenario. So we, as you can see in the Wi-Fi scenarios, the P95 latency reduced the most, 43%. But for the cellular ones, the benefit is still there, but largely reduced. So we infer that in the cellular traces, the performance gains are less pronounced. It's because in the cellular traces, the bandwidth fluctuations are higher. In that case, the congestion control is more to be blamed. So that the ACE algorithm cannot take the real important role. And in the figure on the right shows the evaluation on different video types. And you can see for the game video, the P95 latency reduction can even be larger than 70%. But for the lecture video, the benefit is about 30%. That is because for the game video, there are a lot of movement, and lot of movements come with a lot of fluctuations in the frame size. So in that cases, the ACE will have a better performance. So the experiences here is try to pay attention to the burstness management when the CC performance is already good and the content is various. And in this slide, what I want to show is the experience we had from the paper to the real world deployment. So we had our tests. We firstly have the evaluation on the campus Wi-Fi, and we implemented our algorithm on the WebRTC and the software encoder called the X264. It's a widely used one, and the performance is good. The implementation is fine, and it's really easy to be deployed on the WebRTC. And then we want to move the real-world experiment to the one of our cooperator, the ByteDance Douyin Cloud Gaming. We want to see if the deployment on their online system is also going well. And for the ACN, for the network part, it's deployed very simply. And we have 15% of store wave reduction. And that is very good. But for the AC, for the encoder part, we face some limitation, and that is something I want to share with you. So firstly, in the production services, they usually use this hardware encoder. And for the hardware encoder, it lacks of the control space in the hardware, in the encoding parameter settings. And they always try to set strict rate control. So in other words, they don't want to preserve the qualities. They want to trade the qualities away. So that is something that limits ACE from HC from experimental from the experimental work to the real deployment online. So finally, I'll show you some lessons we got when we want to deploy this ACN online. So first lesson we got is we need to get a clear boundaries with the CCA. This is required. So ACN, the task of ACN is to try to manage the frame level outliers, but it need to build on top of a CCA foundation. So the CCA is a sophisticated design algorithm, and you should trust it. And the CCA determines the target rate set to the video encoder. And ACN should work at a top layer of the CCA. So it should target those those large frame size outliers that is already produced by the video encoder. So that is something we should get it clear. And because for the first time when we want to test it, the engineers, they want to like replace the CCA with a sophisticated design algorithm, but that is not possible. So never try to replace CCA, but try to deal with the outliers. And another experience we have is the carrier throttling. So in the deployment, we face some carrier throttling scenario, especially in the end of the month when the carrier wants to limit your traffic, want to control the traffic. In that cases, the throttling of this the carrier will always come with the shallow buffers. So the buffer in the network will be set really shallow. So in that cases, there will be zero burst allowed. And the core idea of this paper is to some extent allow some burst to be sent into the network. But if the carrier wants to control your traffic, don't never try to send any burst into the network, but strictly pacing them. So that is two of the experience we have when we want to deploy the system. And finally, I'll show you the takeaways of what we have learned by doing this project, by doing this RTC improvements. So firstly, in the modern RTC, we should pay attention to this thing. The sender side pacing latency can be a first order problem. So sometimes it's not even the transmission latency itself. The latency itself can come from the sender side. And the second thing is the average bit rate is not enough. We should pay attention to the burstiness. That's why we claim that, or we claim that we should manage the burstiness. And third one, the strict pacing and blind bursting are both suboptimal. We should adapt in between. And final one is for the encoder. The cross-layer control is most useful when it preserves quality rather than trading quality away. If we are using a system that the quality is not important at all, the burstiness will be useless too. So that's all for the presentation. I'm very open to many questions. So if you have any questions to discuss, I'll be really happy. Thank you.
Thank you very much. Thank you. Yeah, we do have time for questions. Question, yes, Christian.
First, let me tell I really enjoy your talk. I mean, it's very interesting. I have been working on problems like that on and off for about 40 years, and it's refreshing to see your approach. The one thing that I've seen in the pacing algorithm that are implemented in transport protocols is that the leaky buckets is typically trained on a pacing delay that happens to be very short. If you look at the default setup for something like BBR, for example, the pacing, the quantum, which is basically equivalent to leaky bucket in BBR, is set to 1 or 2 milliseconds.
Oh.
And so I wondered whether you are using this kind of CC algorithm or you're using something else.
Let me try to ask one question. So what you mean is that like in BBR, the sending time will be 1 or 2 milliseconds. Is that right?
No, that is not that. BBR can send millions of packets if you let it be. But basically, the purpose of those leaky buckets algorithm is that they remember that you did not use the network completely in the past. So they give you the right to send a little bit more now. And the little bit more is, I mean, there's a tension there because if the little bit more is too much, you're going to create a queue in the network, etc. So most of those algorithms are pretty conservative. And the little bit more that they allow is typically the equivalent of 1 or 2 milliseconds of bandwidth. And so what you want here is more like the equivalent of, say, 15 or 20 milliseconds. And that's a big tension there because you also want to do this kind of thing, this kind of trade-off in proportion to the runtime time of the network. Because since the network capacity is changing all the time, you are going to learn the new capacity basically every RTT. So as you learn every RTT, the CC algorithm will not want to give you too many tokens because they are afraid that if it changes in 1 millisecond, in 20 milliseconds, they would have given too much. So there is a big tension. As you said, this kind of stuff should be discussed at the same time that you're doing the. I mean, basically, you should speak to the guys doing the design of the CCA algorithm because there are lots of interactions there that are interesting. But I mean, I really like the idea of what you are doing is essentially trading bandwidth for CPU.
Yes, that's true.
And yeah, that's a very nice idea. That's very good.
Yeah, thank you. So about the CCA question that you raised, I actually think that if you are considering the CCA like BBR, it will be very complicated because the BBR also want to like specify the pacing rate. So for example, the BBR wants to set a congestion window, but it also wants to set a rate of the pacing, right? So if you consider it this way, the BBR would be very complicated. But in our scenario,
it's not that complicated actually. But what you have
yeah.
to do is that they set a pacing rate, and you know queues are always either empty or full.
Yeah.
They are empty if the pacing rate is much lower than the sending rate, is higher than the sending rate, and they are full otherwise. So basically, you just have to read the pacing rate from BBR and make sure that the video is encoded at a slightly lower rate.
Oh yeah. That's true. Yeah. So what I was going to explain is that in like WebRTC like structure, because it's a GCC, right? In GCC is a relatively simple congestion control mechanism. It only determines a rate. So it only determines a rate and set this rate as a target rate to the video encoder. So it never specify how much burst you want to allow in the network. So that is something that I would say.
Yeah, and maybe the solution is to set the target encoding rate lower than the network capacity.
Yeah, that's typically, that's definitely a solution. But that comes as a burst of the quality loss, and that is not something what we want, right?
No.
We want to set it a little bit lower, and the pacing latency issue will never happen. But the quality
okay, look,
is
there are many people in the queue. I don't want to monopolize the queue. Just want to say thank you, and yes, there's plenty of work to do there.
Thank you.
Thanks, Christian. Let's move on. Stuart.
Stuart Herscher from Apple, great presentation, thank you. I found the paper online, I'm going to print it out and read it. I think there is much interesting work to explore in this space. I've talked with other people running into similar problems with L4S getting deployed by Comcast and other operators right now. It's great for keeping latency low, and part of the way it keeps latency low is by encouraging flows to deliver smooth traffic. And if you mark your traffic ECT1 to opt into the low latency flow, but then send big bursts, you're kind of cheating and not being a good citizen, so you get penalized. And I think we as a community don't yet know the balance there, because as somebody writing a video app, there's a great tendency to say, I have my frame, I want to get it where it's going as fast as possible. My computer's got a 10 gig Ethernet, so I'm just going to dump it out as fast as I can and let the network deal with queuing it and getting it there. And that works today. But with an L4S network, the network is liable to say to you, you're being a bad citizen. So you get penalized by the queue protection function. So it becomes important. If applications want the benefit of low latency, they have to pace their traffic appropriately. And so that's why I find this really interesting, is to know what is the right amount of pacing to get that balance right. So thank you.
Thank you. Yeah, this is also something I didn't think about before.
Okay, next one in line, Mike. Remote.
In line.
Can't hear you yet.
Hello. Yes,
Hi.
thank you.
Yeah, I can hear you.
Do you see me? Right. Thank you for the presentation. This was excellent. I also plan to get a copy of the paper, and maybe that will answer my questions. But while I have the opportunity to ask directly, the 15% stall rate reduction that you saw in the cloud gaming setup, was that just from the network side of the application of this work, ACE-N?
Yes. Yes, that's true, because we didn't really get the SC deployed, unfortunately.
That's very impressive. And one further question, what techniques are you using to estimate the bottleneck buffer size in the network?
It's actually a very simple strategy. So you can, anyways, you can calculate it by a delay multiplies by a rate, right? Because the queue size can be calculated by a delay multiplied by a rate. So the delay we select is the mean RTT, and the rate we select is the network capacity. So we use the simple but efficient algorithm to calculate network capacity. It's the algorithm similar to the packet train or packet pairs. So we just using the, you can consider I'm using the packet pair to calculate the rate. So I can get a more accurate network capacity, and I times it with the mean RTT, and I finally get the rate. So I think this is widely used techniques to estimate the queue size in the network, and we just borrowed the idea.
Very cool. Thank you.
Thank you. And
thank you very much.
Next one is James. Also online.
Oh.
James, do you want to ask a question?
It's getting.
Coming on. So there are some problems with your microphone. We cannot hear you. Sorry, I actually, what's this?
I cannot hear a word.
Sorry, James, there's something wrong with your microphone. We can't hear you. So I suggest we, no, sorry, it doesn't work. James, please reach out to Xiangjie offline and ask your question. Sorry about that. Okay, don't run away. Let's thank Xiangjie once again.
Yeah.
Thank you. Very great talk. Thank you very much. Can you stay after the session for another photo? Oh, of course. Okay, great. Yeah, so okay, yeah, thanks. Thank both of you to the great presentations. Let's move on and resume our discussion from yesterday. So, yes, I'm not sure whether everyone was in the IETF Open session yesterday, but so we had a session that was discussing internet working challenges for AI. And so I just want to present the results and enable a bit more discussion about this. So we had 3 talks yesterday, so on different topics that we felt both kind of could lead to quite interesting research challenges that go beyond like the current engineering that we see in let's say in other places. So we had one presentation by Mingxing Chang on the disaggregated architecture for LMM inference. So something that came out of the Kimi K2 design that's using a KV cache-centric disaggregation architecture. And so that the talk about the design and the using this in a single data center environment, but it was also alluding to scaling this up and to more distributed settings for workloads beyond like one data center. And the second talk was by Hong Xu on reliability engineering challenges in networking for AI. And so discussed many things So, failure detection and measurements and so on. And also brought up the idea of having better testbed and benchmark systems in this space for evaluating systems better, for performing reproducible experiments. And then finally we had a talk by Lisha Zhang on AI agent networking. So that took a more principled position on important naming, identity, and trust delegation topics. So I'm sure you could not avoid all the agentic AI discussions in the side meetings and this week. There was also the BOF this morning. So it turns out that so in this last talk, it turns out that there are many mechanisms that are being discussed these days. So using DNS for discovery and looking up additional properties and so on. But fundamentally, what's really important is to establish trust, leveraging like a human readable established and namespace such as the DNS namespace, and then being able to delegate trust on a fine granular basis because there will be many agents and you want to authorize them really carefully and so on. So that was the idea behind that talk. And so what we kind of distilled from these discussions at the meeting was so mainly these three topics that people felt could be quite fruitful for further research to study, so or to work and develop. So like the testbed benchmark and also data set topic, that seems to be a very good activity that is difficult for like other groups like in the IETF or even like individual academic papers to do. So if there was a chance to develop such frameworks, enabling experiments, benchmarking new systems, so we believe that that could be really quite useful for the community. Then this principled naming, identity, trust delegation concept that I just talked about. So this would require some more principled research to develop solid foundations. Of course, also do experiments with these systems that would go well beyond the current engineering efforts as well, as far as we understand them at the moment. And then thirdly, so this is a space where distributed computing and networking expertise has to come together to think about a co-design of these architectures. So the KV cache-centric architecture is just one example where you really need to understand networking performance, distributed systems concepts, storage to some extent. And so one other topic that came up in Mingxing's talk is like a unified transport that is able to deal with like heterogeneous hardware systems and also networks in the end. And so these were the main three things in like our observation that came out of this meeting yesterday. And now I'd like to open the floor for further comments, ideas on this. Maybe people had other or additional observations that would like to share. And I see right in the queue. Yeah.
Sure, why not? I always have comments and questions. The thinking big picture here, I think it's actually a really exciting time again in systems architecture and implementations for a bunch of reasons, even though, you know, my own research direction is out in a different direction these days. And so I'm more of a dilettante in this than I was a couple of decades ago. But I'm not sure to what extent we have to drag the buzzword AI into everything. This seems to be sort of a little broader than just AI as an issue, particularly when you think about, you know, a lot of the work on re-architecting things around microservices and allowing them to relocate within the network and the orchestration of in-network computation and all of these things. And the only thing that I can really see from a systems point of view that's really dramatically different in terms of that workload is the fact that the LLMs represent a very large investment in both data and computation that's maybe a little harder to migrate around than some of these things. It may just be that an LLM represents such a large and harder to divide chunk of state and data and work that maybe we can't migrate it, in which case maybe we don't have quite as many of those issues as we actually have with the smaller microservices. I don't know, just thinking off the top of my head.
Yeah, surely. I mean, of course, you could be more specific also, right? So, I mean, when we say AI, what we often mean is, you know, collective communication abstractions, and but this may not be the only, you know, class of interactions that we could investigate. Yeah. Dave.
Dave Blanco, WiskNet. I like thanks for doing this summary, Dirk. The second one is the one that's most interesting to me, and you coded it as trust delegation. I don't see any opportunity for trust delegation. It's more trust in delegation, or where does the responsibility lie when the agents are delegated things? What I mean by that, in Hongshu's presentation and in Lisha's presentation, both of them seemed to touch on things about what the researcher's role or what would be the person's role be in these kind of systems. That's a meta level thing that I think a lot of people in the IETF groups, I haven't heard, so I shouldn't speak for them, but I think they might focus on some of the meat of how the AI systems work in networking. And I wonder if we should make sure we think about the part about what the role is of the researcher. Are they just in the evaluation phase? Are they in the design phase? How do they handle that they are really responsible for what those agents do afterwards? And maybe the simple idea is, what's the parallel in this of like security considerations and privacy considerations? Where are the responsibility considerations so that you don't delegate trust to something that can't be trusted? It's definitely a meta thing, so I don't know where it goes in the IRTF, but I want us to kind of think about and work through that, because I'm scared of any talk where they don't talk about what the roles are, and they don't talk about the trust delegation, and they don't talk about how you can't delegate trust. You have to keep the responsibility with the person that deployed the thing.
Okay. Yeah, thanks. Good point. Brian, remotely?
Yeah. Ooh, wait a minute. Hold on. I'm on the wrong camera. Let me come over here then. So yeah, +1 to both of those points. I think of the three things here, the most interesting thing, and I think the hardest nut to crack, is this principal naming, identity, trust delegation in a way that it will deploy, right? Like, so I was really, really inspired by Leisha's talk yesterday, and I had spent most of the day trying to do my day job thinking about sort of the outcomes of that. And there's some engineering in the IETF that's like nibbling at the corners of this, I think. So like the WIMSA working group, I missed it this time. I'm not sure if there's anyone who was here, who was there, like looking at the fit here, but like the trust responsibility delegation, there's another missing primitive, I think, in the IETF stack that's like the on behalf of, right? It's like, it's not just me, it's not just you or the agent or whatever. And I think that this will be, there's a lot of attention on AI at the moment. I'm not sure how long that lasts. Maybe for a very long time, maybe for a very long time at a lower intensity. But I think there are fundamental issues that we should dig into. And it would be a shame if we tied that to a part of the problem. So I think AI shows us that there's a challenge here. But I look forward to essentially working on the challenge that Leisha set to us yesterday.
Okay, thanks, Brian. And okay, we have another remote question. Not sure it's from Wes or it's from the room. It's actually from, okay, Wes.
Yeah, I think the second one is sort of the interesting case that we need a lot better definition before you dive into it. Specifically, you need sort of the gap analysis that I don't think is being done with the things that are in there right now. You know, we have really good naming systems. The only thing that we don't do yet is naming on the client side, which really becomes the AI agent side, except that there are some work in that. I mean, I chair dance, so that's a good example of where engineering has been done lately to do that kind of thing. You know, there's been a lot of discussion about identity. What people haven't aligned yet is how this is different from, you know, the token-based authentication mechanisms that we hand to a bunch of software today, like, you know, when we create an account, then we hand out tokens to things. Why does that not work for agents? I'm not saying that it doesn't, right? But nobody's really done the analysis yet for where is the new thing that really becomes research. You know, trust delegation almost seems like a legal framework, but as I mentioned to people the other day, we're already doing trust delegation all over the time, right? When you have your home automation system with whatever company it is that creates that, you're delegating it the OAuth 2 like credentials or whatever to turn on your lights. So there's already a bunch of agents that do that. We're just empowering the agents to do a lot more than we ever have before, and it's no longer rule-based. It's, you know, some other black box decision-making ability. But there needs to be a really good analysis for what's new there that can't use the existing engineering pieces. And again, I'm not saying there aren't any, but until I see that, it's hard to really figure out this is an area that we need work in first, if that makes sense.
Okay, thanks. I think Lisha can answer part of these questions.
I was actually came here to answer Rod's question, but for Wes, I think for the token stuff, that works great as of now. For AI, I think about if you have delegations, there's 3 levels deep. I was wondering where your OAuth server would be and how many of them you would need. For now, we only have with 1 level of delegation. If you go further down, like an agent can delegate someone other agent to do things and further on. And I wasn't sure how today's system would work. But back to Rod, I actually agree with Rod. We are facing a system challenge. Yes. And I just want to explain why the word AI is relevant here. That is because it changes the system quantitatively in terms of scale and the dynamics. As I mentioned, I forgot whether it's Monday or Tuesday, that today we already have billions of internet users and tens of billions of devices. So therefore, it's not that number as important. People talk about, oh, we're going to have billions of agents, so it's a bigger problem. It's that how those numbers work. We call today's internet users eyeballs. Eyeballs don't interact with each other. They all watch onto the sky, there's a cloud there. But the agents changes that nature because the agents are supposed to be collaborative, working together. We never work together directly. Like I mentioned, this example right before I got onto the plane, I was dragged into a dinner with a bunch of people who want to use agentic system to help them develop some application-specific use cases. So they asked me the question to say, why can't our agents talk together as a group? Because we already have that, like a WhatsApp group. I mean, I should give them credit that they're not networking people. So therefore, they didn't know all today's group-based applications work in the cloud. They didn't mean their agent needs to talk to the cloud to get a group behavior. But that's how we do grouping today. And I don't think that's going to work for agents, especially talk about physical agents. They cannot afford that delay. And there's also the scalability question, how many agents out there and how the cloud actually going to deal with that. I was joking with someone during the lunch that 3 robots in the manufacture floor, you have to consult the cloud to get tokens. Before you get tokens, you already smashed into each other. Then how you repair from that crash? So I agree, it's really a system challenge. But so far we have dealt with by the great cloud. And I think agent will push us to a new solution to be cloud independent. Thank you.
Thank you. And we have Christian again.
Christian Wiedemer. Yeah, I mean, I think we have a real issue there. I am a bit concerned when I see the IRTF of these 3 options focusing on the naming issue. Because, you know, it feels like the old story of the philosopher that has lost his key and is looking for the key under the lamppost. And he says, hey, yeah, I know it didn't fall there, but here I have light and I might find it if it did fall there. And naming, identity, that are things we've been working on for many, many years. And they are certainly useful. And I like the work that went on in Dinergy, and it's very nice. But let's face it, the big problem we have with this system is that these are massively centralized systems today. And they are massively centralized because it takes billions to train a new model. And that's the big, big problem. And so what would like to see? What we would like to see is some kind of movement in which this kind of huge task is broken in little pieces, and we can enable that. And the little pieces that enable that are things like, yeah, I mean, the point 1 and 3 actually. So I am a bit concerned about remaining under the lamppost when the big problem is somewhere else.
Okay, thanks for this perspective. I get what you're saying. I mean, of course, there's you know, this massive infrastructure scale and centralization in the systems today. On the other hand, for the agent communication, okay, we don't know all of this yet, but so agents are the kind of distillation of the training. Like these are inference systems. They may use centralized inference, but not necessarily. So there are also open source models and so on. So there might be you know, also potential for, you know, other system architectures. Although of course I agree, we see the tendency towards centralization. Thanks, Christian. And we have Wes again.
Yeah, I think that the other thing the IRTF has to consider is the IRTF is not a quick moving thing, right? The problem space of the IRTF is 5-10 years out, maybe. And which elements of this will not be handled by the commercial organizations on a much faster timeline because they need it tomorrow. And so I think that the harder problem in this entire list is which elements of that are not going to be handled, right, without something like the IRTF doing a cross collaboration, large scale, long-term, solution versus the industry is going to actually have to solve this problem and solve it quickly on their own anyway. And there's no way the IRTF can actually even participate in that discussion.
Right, I get it. On the other hand, I mean, yes, so like yesterday's presentation, so like, for example, Hongshu's work, I mean, is of course also with industry collaboration, but having people, who bring the state-of-the-art work here, enable more discussion, maybe, and also enable like analysis of some problems, that could potentially still be useful, I think. Alicia again. Alicia, you're in the queue. Do you want to say something?
I just want to get back to Wes on his questions. I think there are two comments here. Number one, if the industry go down the direction we believe is the right direction, so much the better. Yes, I agree. They have more power, more money, whatever. They have more pressure to get the work done. But I think like the second bullet about this naming using the DNS name or derived name from DNS, the unifying namespace. I haven't seen the industry actually mentioning that. And also the concept of local trust. I haven't seen that yet. So therefore, I think the IRTF really trying to explore the direction of research. If the industry agrees with it, that's so great. I also want to make a clarification. IRTF is not doing the research per se. I think we're a coordination platform where individual teams bring the research result here for exchange and further development. We're not coming here 3 times a year to do the research per se. And for that, I believe it will be very slow.
Lars.
Lars Mozilla. So I want to agree with the last thing that Lisha said. So stepping back a bit or stepping up, or however you want to think about this. So I think AI is a huge topic both in industry and in academia at the moment, right? And the IETF struggles to identify pieces that are ready for standardization. But I think it would be very useful for the overall IETF, IRTF family to have a venue in this space, to give people the opportunity to come and present relevant work either from industry or academia, right? If we tried this a couple of times for other big fuzzy topics, like we had an NFVRG a while ago, we had an SDNRG. Those functioned okay for a while and then they didn't. And this potentially has the same problem. But that problem is, I think, fixable by having extremely diligent chairs that make sure that what gets presented actually is of interest to many and actually brings in new ideas or new thoughts or new things from industry, right? So I think it's research groups much more than working groups live and fall with the chairing, and this will be, if we did something in this space, would be even more so than many others. But I think it would be useful to the overall IETF if we had something that for people that are interested in AI, and many people are at the moment, to come and participate in. I think I talked to you, Wes, actually, yesterday. So Wes runs the guides program where new participants can get paired up with a mentor. And we had apparently very many that asked for a mentor to guide them to AI topics in the IETF. And we have very few mentors or topics where we can guide those people to. So I think a venue like this would be helpful for the org. Thank you.
Thanks, Lars. So we can take 2 short statements, one from Wes and one from
mine's very quick. Lisha, you and I agree. I agree. The IRTF is not where research is done. It's where research is reported. And I absolutely agree that finding some long-term novel research things to present in a group, just like is what happens in MapRG, is a wonderful use of the IRTF. The trick is doing things that you can get enough interesting long-term sort of research results that are novel as opposed to this is what industry just did, I think is the hard part.
Okay. Thanks, Wes. Colin.
Hi, Colin Perkins.
There's the camera.
Oh, there's the camera. All right, I'm looking in the wrong place. So yeah, I think I agree with a lot of what has been said. Where the IRTF offers the most benefits is when it connects the researchers and the standards community. One aspect of that, perhaps the passive aspect of that, is in allowing people to come and present work which has happened elsewhere and make the standards community aware of the research which is happening, the interesting research that's happening, and make the academic research community perhaps aware of some of the issues which are happening in the industry. And I think a group like, as you said, MapRG style is potentially very useful there. Where I am perhaps more struggling to see where we can offer value is in the more active coordination of research. And I think that's, as someone said, it's something which has to take place on a longer time scale to avoid just being completely overtaken by events. And I think that's something where we need to think a little harder.
Okay, great. Yeah, thanks everybody for this discussion and really valuable points. So we'll take this in and continue this discussion. So there is a mailing list that could be used for further discussion. Please try to get on this. I will also send another message on IRTF announce on this one. And that would conclude the meeting today. Thanks, everybody. Great meeting. See you soon. And Shangji and Tianyi, can you come to the front? Okay. Oh, okay, of course. Okay. How about